Morning to one and all. This is Dr. Padma, Assistant Professor, Department of Physics, Institute of Aeronautical Engineering. Today our topic is Avalanche Transit Time Devices. Outline of the topic is Introduction to Avalanche Transit Time Devices, and we will discuss about the impact diode, trapped diode and barrier diodes. First one, what is Avalanche Transit Time Devices? So, Avalanche Transit Time Devices are the PN junction diodes with highly doped P and N regions. For example, this is PN junction diode. So, avalanche transit time devices are also the PN junction diodes. So, in PN junction diodes, in P region and N region, both are heavily doped. So, avalanche transit time devices are the PN junction diodes. In PN junction diodes, in the P region and N region both are highly doped. So, they could produce a negative resistance at the microwave frequencies by using carrier impact ionization, avalanche breakdown and carriers drift in the high field intensity region by using reverse biased conditions. So, the avalanche transit time devices produce a negative resistance. So, here they produce negative resistance at microwave frequencies. So, avalanche transit time devices produce a negative resistance at microwave frequencies by using the carrier impact ionization. Here we are using carrier impact ionization, avalanche breakdown process and carrier drifts. Those are operated in the high field intensity region by using the reverse biased conditions. So, there are three types of devices are available. In that, first one is the impact ionization avalanche transit time effect, which is simply called as the impact diode. Second one is the trapped plasma avalanche triggered transit effect. So, this is simply called as the trapped diode. Third one is the barrier injected transit time effect, which is known as the barrier diode. So, avalanche transit time devices means those are also PN junction diodes. Here, P and N region both are heavily doped. Due to heavily doped, they produce a negative resistance at microwave frequencies. Here we are using the impact ionization, avalanche breakdown and carrier drifts in the high field intensity region by applying the reverse biased condition. So, here the three types of devices are available. First one is the impact ionization avalanche transit time effect, which is known as the impact diode. Second one is the trapped plasma avalanche triggered transit effect, which is known as the trapped diode. And third one is the barrier injected transit time effect, which is simply called as the barrier diode. First one is the impact diode. So, in impact diode is now one of the most powerful solid state sources for the generation of the microwaves. So, to generate the microwaves, impact diode is the one of the most powerful solid state devices. So, it can generate higher CW power. CW power means continuous wave power outputs in millimeter wave frequencies, that is above 30 GHz for all solid state devices. So, the impact diode is the one of the most powerful solid state sources for the generation of the microwaves. It can generate the power outputs in millimeter wave frequencies, that is about 30 GHz for all solid state devices. So, these are the compact, inexpensive, moderately efficient and with improved device fabrication technology. So, these diodes also have become reliable under high temperature operations. So, these are the compact and inexpensive and moderately efficient with improved device fabrication technology. So, these diodes also have become reliable under high temperature operations. So, for high temperature operation also these diodes are the reliable. The salient features of the diodes are as follows. So, impact stands for impact ionization avalanche transit time. So, impact diode means impact ionization, avalanche transit time. So impact diodes employ impact ionization and transit time properties of semiconductor structures to get the negative resistance at microwave frequencies. So basically here we are getting the negative resistance at the microwave frequencies. So impact means impact ionization, avalanche transit time. So impact diodes employ impact ionization and transit time properties of the semiconductor structures to get the negative resistance at the microwave frequencies. So what is impact ionization or avalanche multiplication? So impact ionization is also called as the avalanche multiplication. So avalanche multiplication means it is a process related to semiconductor in which generation and multiplication of the whole electron pairs takes place to produce the knocking of the valence electrons into the conduction bands by highly energetic carriers when the electric field is increased above a certain value. So the rate of wave production is a sensitive non-linear function of the electric field. So impact ionization or avalanche multiplication means it is a process which is related to semiconductor. Here the generation and multiplication of the electron hole pairs. So the generation and multiplication of the electron hole pairs are produced due to the knocking of the electrons in the valence band that into conduction band by highly energetic carriers when the electric field is above the certain value. So if you increase the electric field from a certain value, then it is knocking of the valence electrons into the conduction band by highly energetic carriers. Here the electric field is increased above a certain value. So the rate of the pair production is a sensitive and non-linear function of the field. So the negative resistance occurs from the delay which cause the current to lag behind the voltage by half cycle time have two components. So the negative resistance occurs from the delay. Due to the delay, the negative resistance is occurred which cause the current to lag behind the voltage. So which causes the current lagging across the voltage by half cycle time. By using half cycle time, it has two components. So the negative resistance occurs from the delay. So the negative resistance is occurred due to the delay which causes the current lagging across the voltage by using the half cycle time. So one is the avalanche time delay caused by finite build-up time of the avalanche current. The first one is the avalanche time delay. So the negative resistance is occurred due to the time delay. So in that first one is the avalanche time delay which is caused by the finite build-up time of the avalanche current. So the other one, the second one is the transit time delay by the finite time for the carriers to cross the drift region. To cross the drift region, it has the transit time delay. First one is the avalanche time delay which is caused by the build-up of the time of the avalanche current. So the avalanche time delay is caused by the avalanche current. Then second one is the transit time delay by which is caused by the finite time for the carriers to take the time to cross the drift regions for the carriers. So these diodes are made from gallium arsenide, germanium and silicon. So impact diodes are fabricated with gallium arsenide, germanium or silicon. Extremely high voltage gradient. The high voltage gradient is 400 kilovolts per centimeter. Back biasing the diode is required for its operation. Here back biasing is used for the operation of the diode. In all the structures there exist two regions. So for all the structures there exist two regions. First one is the avalanche region. So for all the structures here exist two regions. Those are first one is the avalanche region, second one is the drift region. So avalanche region means in this region avalanche multiplication takes place. Doping concentration and field intensity will be very high. In avalanche region, avalanche multiplication takes place. Avalanche multiplication means it produces the electron hole pairs. So in avalanche region, avalanche multiplication process takes place Here the doping concentration and field intensity will be high. The second region is the drift region. In this region, avalanche multiplication does not take place. The doping concentration and field intensity levels are low. So the depletion region is the avalanche region plus drift region. So here the depletion region generated due to the avalanche region and drift regions. So for every structure, here two regions are available. So first one is the avalanche region. In avalanche region, avalanche multiplication process takes place. Here the doping concentration and field intensities will be very high. Second one is the drift region. In this region, avalanche multiplication does not take place. The doping concentration and field intensity are very low. Here the depletion region means this is the avalanche region plus drift region. So this is the impact diode structure. First one is the silicon. By using silicon, we can fabricate the impact diodes. So first one is the avalanche region. Here this arrow shows the avalanche region. So in middle one is the space charge region. Here the drift region is generated. So in this region, this is the inactive region. So this one is the avalanche region. This region is the inactive region. So here the drift region. So here the depletion region or space charge region means avalanche region plus drift region that will produces the space charge region. So it can be shown that the maximum resistance occurs when the transit angle theta equal to pi. When the transit angle theta equal to pi, here the negative resistance is occurred, at which the operating frequency will be F equal to Vd by 2L, where Vd is the drift velocity of the carriers and L is the length of the drift region. So its operation is illustrated in the figure. So it can be shown from that. The maximum negative resistance occurred when the transit angle theta equal to pi, at which the operating frequency becomes F equal to Vd by 2L, where Vd is the drift velocity of the carrier and L is the length of the drift region. So the impact is the name of the diode family. So impact means which is the name of the diode family. Its basic members are, first one is the reed diode, P plus N I N plus. So and its dual N plus P I P plus regions. So reed diodes means it has the regions P plus N I N plus, or it's a dual N plus P I P plus. The single drift diode, that is P plus N P plus. This is the single drift diode, P plus N P plus. Double drift diode, which is also called as the R impact diode. Double drift diode means R impact diode. So R impact diode means P plus P, N, N plus. And pin diode, already we discussed pin diode, photo intrinsic, P-type intrinsic N diode, that is P plus I, N plus. So impact is the name of the diode family. So the basic members of the diode family are, first one is the reed diode. Reed diode means P plus N I N plus, or its dual, that is N plus P I P plus. The single drift diode is P plus N P plus. So double drift diode are also called as the R impact diode, that is P plus P N N plus diodes. So last one is the pin diode, P-type intrinsic N-type diode, P plus I, N plus regions are there. The noise measured in gallium arsenide is low when compared to silicon. By comparing with the silicon, the noise measured in gallium arsenide samples are low. And for germanium, it is in between gallium arsenide and silicon. So the noise measurement in gallium arsenide is low when compared to silicon. For germanium, the noise measurement is in between the gallium arsenide and for germanium, it is in between the gallium arsenide and silicon. The main reason for the low noise behavior of gallium arsenide is that for a given field, the electron and hole ionization rates are essentially same. Whereas in the silicon, these are the quite different. So the main reason for the low noise occurred in the gallium arsenide is that for the given electric field, the electron and hole ionization rates are same. The electrons and All ionization rates are same, but in the case of silicon, those are the different. That is the main reason for the low noise occurred in the gallium arsenide. The highest powers, frequency and efficiency are obtained from the double drift diodes that are known as the R impacts. So the highest powers, frequency and highest efficiency are obtained from the double drift diodes compared to single drift diode. Those are known as the R impact diodes. The power frequency product is highest for these diodes. The power frequency product is also higher for these diodes. The improved performance results mainly from the fact that holes and electrons produced by the avalanche are allowed to give the energy to RF signals while traversing the drift region. So, the improved performance results mainly from the holes and electrons. Those are produced by the avalanche effect. The holes and electrons are produced by the avalanche effect. Those are allowed to give the energy to the RF signals while traversing the drift region. In the case of single drift diodes, only one type of carriers is utilized. So, for the case of single drift diodes, we are using only one type of carriers, either electrons or holes. So, the highest powers, frequency and efficiencies are obtained for the double drift diodes, which is also known as the R impact diodes compared to the single drift diodes. Comparison. When compared to gun diode, these diodes have more efficiently around 30%, more powerful around 15 watt CW power, and their frequency can reach up to 200 GHz, whereas in the case of gun it is only 100 GHz. So, when compared to gun diode, impact diodes have more efficiency around 30%. Compared to gun diode, it has more efficiency, that is around 30%, and more powerful, which is around 15 watts CW power, and the frequency can reach up to 200 GHz, whereas in the case of gun diodes, it is only around 100 GHz. But when compared to gun diodes, these are the noise. Noise is more in this impact diode compared to gun diode. Below 40 GHz, gallium arsenide impact diodes have high powers and efficiency than the silicon impact diodes. So, compared to silicon impact diodes, gallium arsenide below 40 GHz frequency, the gallium arsenide impact diodes has the high powers and efficiency compared to the silicon impact diodes. Between 40 to 60 GHz, gallium arsenide impact diodes show high power and efficiency, whereas silicon impact diodes give high reliability and yield. So, between 40 to 60 GHz, gallium arsenide impact shows high power and efficiency, whereas silicon impacts give high reliability and yield. Above 60 GHz, silicon impact diodes outperform the gallium arsenide impacts. Above 60 GHz, silicon impact diodes are more better than the gallium arsenide impacts. Around the frequency 10 GHz, the efficiency is closer to 40%. So, above 60 GHz, silicon impact diodes are the outperform the gallium arsenide impacts. Around the frequency 10 GHz, the efficiency is close to 40%. The power output. At lower frequencies, the power output is thermal limited and is inversely proportional to the frequency varies. So, at lower frequencies, the power is inversely proportional to the frequency. So, at lower frequencies, the power output is thermally limited and which is inversely proportional to the frequency, that is varies as 1 by F. At higher frequencies means greater than 50 MHz, the power is electronic limited and varies as F square. So, at lower frequencies, the power is the thermally limited, which is inversely proportional to frequency. At higher frequencies means at greater than 50 MHz frequencies, the power is the electronic limited and it varies as the F square. Drawbacks of the impact diode. The noise is high mainly because of the statistical nature of the generation rates of the electron hole pairs in the avalanche region. In avalanche region, electron hole pairs are generated. Due to the electron hole pairs generation, the noise is more in the impact diodes. So, which are highly sensitive to operational conditions. So, impact diodes are sensitive in the operational conditions. Large electronic reactance which can cause detuning or even burnout of the device unless proper care is taken. So, which are sensitive. So, impact diodes are sensitive. That's why large electronic reactance which can cause the detuning of the diodes or the burnout of the devices unless the proper care is taken. So, the proper care will be necessary for the impact diodes. Applications of the impact diodes. So, impact diodes are at present the most powerful CW solid state microwave power sources. So, impact diodes are present the most powerful CW solid state microwave power sources. The diodes have been fabricated from germanium, silicon and gallium arsenide and can be probably be constructed from other semiconductors as well. So, the diodes mainly fabricated by using germanium, silicon or gallium arsenide. So, impact diodes provide potentially reliable, compact, inexpensive and moderately efficient microwave power sources. They are generally used in the microwave links and CW radars. So, impact diodes are mainly used in the microwave links and CW radars in electronic countermeasurements. So, impact diodes are present the most powerful CW solid state microwave power sources. These are the microwave power sources. The diodes have been fabricated using either germanium, silicon or gallium arsenide. So, impact diodes provide potentially reliable, compact, inexpensive and moderately efficient microwave power sources. They are generally used in the microwave links, in CW radars, in electronic countermeasures. Second one is the trapped diode. So, trapped diode is the another diode used in the generation of the microwave signals, which has a very complicated design methodology and functioning. So, the design and methodology and functioning is complicated. So, trapped is the other diode used in the generation of the microwave signals. So, trapped diode is also used for the generation of the microwave signals, but here the operation is very complicated, design methodology and functioning is complicated. It is high efficiency microwave generated capable of operating to several gigahertz. So, which can be operated at higher frequencies, that is several gigahertz. So, it has high efficiency microwave generator. So, the basic operation of the oscillator is a semiconductor PN junction diode reverse bias. Under reverse bias, to current densities well in the excess of those encountered in the normal avalanche operations. So, the basic operation of the oscillator is semiconductor PN junction diode which is in reverse bias to current densities well in excess of those are encountered in the normal avalanche operations. So, high peak power diodes are structures with n-type depletion region width varying from 2.5 to 12.5 micrometers. So, here the n-type depletion region width varying from the 2.5 to 12.5 micrometers. The doping of the depletion region is generally such that the diodes are well punched through the breakdown. So, the doping of the depletion region is generally as usual as the diodes are well punched through the breakdown. So, the device's P plus region is kept as thin as possible to 2.5 to 7.5 micrometers. So, the devices, in the devices, the P plus region must be kept as thin as possible at 2.5 to 7.5 micrometers. So, the trapped diode's diameter ranges from as small as 50 micrometers for CW operation to 750 micrometers at lower frequency for high peak power devices. So, the trapped diode's diameter ranges from as small as 50 micrometers for CW operation to 750 micrometer at low frequency operation for high peak power devices. So the diameter ranging in between 50 micrometers to 750 micrometers. So some important points worth noting about these diodes are mentioned as TRAPET stands for Trapped Plasma Avalanche Triggered Transit Devices. TRAPET means Trapped Plasma Avalanche Triggered Transit. TRAPET stands for Trapped Plasma Avalanche Triggered Transit Time Devices. So, TRAPET diode is high power, high efficiency device. So the design and performance of the devices are highly complicated because of the strong device circuit interaction that dictates most of the device performance. So here the design and performance of the TRAPET diodes are highly complicated, which is due to strong circuit interaction that dictates the most of the device performance. So silicon P plus N, N plus or N plus P, P plus structures are used to get high powers. So the doping of the depletion region is generally such that diodes are well punched through at the breakdown. The depletion region extends from P plus N junction to N plus N junctions. So silicon P plus N plus or N plus P, P plus structures are used to get the high powers. So, the doping of the depletion region is generally such that the diodes are well punched through at the breakdown. That is, depletion region extends from P plus N junction to N plus junction. So, this is the voltage and current waveforms for the TRAPET diode. Here we are taking P plus N plus structure. P plus N plus structure. Here from this graph it can shows the voltage and the current on the y-axis. On x-axis we are taking the time. Here the different regions are there. Those are from at point A and point B to C and C to D and D to E, E to F and F to G. Here the different regions are there. Those are known as the charging, plasma formation, plasma extraction, residual extraction, charging. So here different regions are observed from the graph. First one is the at point A and second one is point B to C, C to D, D to E, E to F and F to G. Here different regions are observed. Those are the charging, plasma formation, plasma extraction, residual extraction, charging. Now we will discuss in detail about that regions. First one is the at point A. At point A, the diode current is turned on. So at point A is the initial point, starting point. So at point A, the diode current is turned on. Since only charge carriers present are those caused by the thermal generation. So at initial point, the charge carriers are present, those are caused by the thermal generation. So the diode initially charges up like a linear capacitor. So at initial point, the diode charges like a linear capacitor, driving the magnitude of electric field above the breakdown voltage. So at point A, the diode current is turned on. Since the only charge carrier present are those caused by the thermal generation. So the diode initially charges like a linear capacitor, driving the magnitude of electric field above the breakdown voltage. So, second one is the B2C. When sufficient number of carriers is generated, so at the region B2C, the number of charge carriers are sufficient. So, the particle current exceeds the external current and the electric field is diffused throughout the depletion region, causing the voltage to decrease. So, from point B to C, the sufficient number of carriers are generated. So, the particle current exceeds the external current and the electric field is diffused throughout the depletion region, causing the voltage to decrease. Then second one is the C to D. During this time interval, the electric field is sufficiently large for avalanche to continue, and a dense plasma of electron and holes is created. As some of the electrons and holes drift out of the ends of the depletion region, the field is further depressed and traps the remaining plasma. The voltage decreases to point D. So here we can observe from C to D, during this time interval, the electric field is sufficiently large. So in C to D points, the electric field is sufficiently large for the avalanche to continue, and a dense plasma of electrons and holes is created as some of the electrons and holes drift out at the end of the depletion region. The field is further depressed and traps the remaining plasma. The voltage decreases to point D. So then coming to D to E, a long time is required to remove the plasma. Here it can be taken a long time to remove the plasma because the total plasma charge is less compared to the charge per unit time. When compared to charge per unit time, the total plasma charge is large. That's why it will take more time to remove the plasma. So at point E, the plasma is removed, but residual charge of holes in the other end. So D to E, a long time is required to remove the plasma because the total plasma charge is large compared to the charge per unit time. At point E, the total plasma is removed, but there is a residual charge of holes in the other end. Then coming to E to F region, as the residual charge is removed, here the residual charge is also removed, the voltage increases from point E to F. So from point E to F, the voltage will be increased. At point F, all the charge that was generated internally has been removed. This charge must be greater than at point A. So in E to F region, the residual charge is removed and the voltage will be increased from point E to F. At point F, all the charges that was generated internally has been removed. At point F, all the charges are generated or removed. This charge must be greater than compared to the point A. Then F to G region. The diode charge up again like a fixed capacitor. At a point A, it will be act as a linear capacitor. Then coming to point F to G, the diode charges up like again like a fixed capacitor. At point G, the diode current goes to zero for a half of a period and the voltage remains constant at VA until the current comes back on the cycle repeats. So F2G, the diode charge up like a fixed capacitor. At point G, the diode current goes to zero for half of a period and the voltage remains constant at VA until the current comes back and the cycle repeats. So this diode requires a circuit that can support harmonics of fundamental frequency of high voltage amplitudes. So this diode requires a circuit that can be support the harmonics of the fundamental frequency of high field voltage amplitudes. So the rich harmonic content is necessary to get the required phase delay the current at such low frequencies. So the rich harmonic content is necessary to get the required phase delay in the current at such low frequencies. So drawbacks of the trapet diode, it has higher noise figure when compared to impact diode. So compared to impact diode, it has the higher noise. So its operation is quite complicated and requires a good control over the device and circuits. So here the operation is quite complicated compared to impact diode. So the upper operating frequencies are practically limited to below millimeter wave ranges, that is 10 gigahertz. So the upper operating frequencies are practically restricted or limited to below millimeters wave range, that is 10 gigahertz. It has highly sensitive even to small changes in the circuit or operating conditions or temperatures. So trapet diodes are more sensitive even for small changes in the circuit or operating conditions or the temperatures. Performance of the trapet diode. The output power of series connection of the 5 diodes under pulse condition reaches 1.2 kilovolts with efficiency of 25%. So the output power of a series connection of 5 diodes under pulse condition reaches 1.2 kilowatts with a efficiency of 25%. The upper frequency limit is close to 10 gigahertz and the highest obtained efficiency is 75%. So the upper frequency limit is close to 10 gigahertz and the highest obtained efficiency is 75%. So its high pulse power output is much larger than most other microwave semiconductor devices. So it has the high pulse power output which is much larger than the most of other microwave semiconductor devices. And last one is the Barrett diode. Barrett stands for barrier injected transit time diodes. Barrett diodes means barrier injected transit time diodes are the latest addition to the family of the active microwave diodes. So these diodes are the latest diodes in the microwave diodes. So Barrett stands for the barrier injected transit time diodes. So they have long drift regions similar to those of the impact diodes. So they have long drift region. So here the drift region is lengthy compared to the impact diodes. They are formed by the forward biased PN junction diodes. So impact diodes and trapped diodes are formed under the reverse biased PN junction. But coming to the Barrett diode, which are formed due to the forward biased PN junctions with PNP, PNIP or PN metal or metal N metal configurations. These are the configurations used in the Barrett diodes. First one is the PNP, P-type, N-type, P-type. Second one is the PNIP and the third one is the P-type, N-type. Here one metal is used, PN metal. And the last one is the metal N-type metal configurations are available in the Barrett diodes. So the carrier traversing the drift region of the Barrett diodes, however, are generated by the minority carrier injected from the forward biased junction instead being extracted from the plasma of the Avalanche region. So here the carrier traversing in the drift region of the Barrett diodes are generated due to the minority carrier injection from the forward biased junction instead of being extracted from the plasma of an Avalanche region. So Barrett diodes are much less noisy than the impact diodes. So compared to impact diodes, Barrett diodes are less noise. Noise figures are as low as 15 dB. So 15 decibels at a C-band frequencies with a silicon Barrett amplifiers. So the noise figure is as low as 15 decibels. The major disadvantage of Barrett diodes are relatively narrow bandwidth and the power outputs limited to a few milliwatts. So the major drawback or the major disadvantage of Barrett diodes are relatively which are in narrow bandwidth and the power output is limited to very few milliwatts. Principle of operation. So minority carriers are injected into the drift region. So minority carriers are injected into the drift region. The transit time through the drift region provide the required phase shift between the current and voltage to give the negative resistance. So here the main process is the minority carriers are injected into the drift region. The transit time through the drift region provides the required phase shift. The phase shift between the current and voltage which will give the negative resistance. So when the diode is mounted in a resonator, a noise spike generates microwave voltage across the diode. During the positive half cycle, the total voltage produces sharp pulse of minority carrier current in the drift region. When the diode is mounted in a resonator, a noise spike generates the microwave voltage across the diode. During the positive half cycle, the total voltage produces a sharp pulse of minority current in the drift region. During the drift time, a constant external current delivers the energy to the resonator from the DC bias source to maintain a continuous oscillation. So during the drift time, a constant external current which delivers the energy to the resonator from the DC bias source to maintain a continuous oscillation. So this is the metal N-type metal barrier diode. Here, this one is the metal, this one is the metal. In between the two metals, we are taking the N-type region. So this one is the metal N-type metal barrier diode. So this one is the energy band diagram in the thermal equilibrium positions. The energy band diagram of the barrier diode at the thermal equilibrium position. So here the energy band under the bias conditions. So this one is the electrons and holes. So the barrier diode, the energy band diagram under the bias condition. Applications. Barrier diodes are low power, low efficiency and less noisy devices. So barrier diodes are low power and low efficiency. It has the low efficiency and less noisy devices. They are used in the local oscillator at microwave frequencies. So those are used in the local oscillators at microwave frequencies. So the comparison between the gun diode, impact diode, trapper diode and barrier diode dividers. So these are the parameters. So first one is the operating frequency. Operating frequency for gun diode is 1 to 100 GHz. Impact diode is 0.5 to 100 GHz. Trapper diode is 1 to 10 GHz. Barrier diode is 4 to 8 GHz. The bandwidth is 2% of center frequency for gun diode. In impact diode, 10% of the center frequency, and in barrier diode, which is a narrow bandwidth. Power output. So few milliwatts CW made is 100 to 200 watts pulsed. So in impact diode, 1 watt CW mode for 400 watt pulsed mode. So several 100 watt pulsed mode. So low milliwatt power. So efficiency for gun diode is low. For efficiency for the impact diode is 3% CW for 60% pulsed. 20 to 60% pulsed for the trapper diode and low for the barrier diode, that is 2%. Noise figure, so high 30 decibels for impact diode, which is high for trapper diode, that is 60 decibels, and low for barrier diode, which is less than 50 decibels. Application. So gun diode can be used as the oscillator. Impact diode is also used as the oscillator. Trapper diode is also used as the oscillator. Barrier diode can be used as the local oscillators. These are the applications. So basic semiconductors used for the fabrication for gun diode is gallium arsenide or indium phosphide. So for impact diode fabrications, we are using silicon, germanium, gallium arsenide and indium phosphide. For trapper diodes, we are using only silicon. For barrier diodes, either we are using silicon or metals. So harmonics. Harmonics is less for impact diodes, strong for a trapper diode and less for the barrier diode. Size is small in the gun diode, small for the impact diode, and all are small for the trapper and barrier diode. So roughness is yes in the gun diode, all are having the roughness. These are the comparisons between the gun diode, impact diode, trapper diode and barrier diode. So these are the references used for the semiconductor physics, SMG and Flickr Link, microwave and radar engineering. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.